All right, welcome everyone to our video lecture replacing Friday's lecture materials outside of class. So today we're really going to be covering some basic topics on dissolving salts in solution, basic electrolyte behavior tied to activity, the chemistry of solubility, and how that applies to shifts in chemical potential, the solubility product, and how we ultimately use the concept of solubility of ions in solution tied to our basic understanding of electrochemistry and changes in Gibbs free energy according to the Nernst equation. Let's keep moving. So when dissolving salts in water, you are actually causing them to dissolve, and then those solvated species are positive or negative ions. And in the course of the next few boards here, we're going to be investigating the chemistry of dissolution in the way that we'd look at it from thermodynamics perspective. So we've already known that activity is an effective mole fraction, and that we tie that back to the activity coefficient gamma that you see right here. And ionic solutions are relatively unique in that they're very common in our everyday lives, but they're unique as a solution in that they tend to have gammas that are less than 1. Okay? And so if we were to compose again the basic equation for activity of a species I, using Lewis's notation, we would have the activity coefficient times the mole fraction, and the interesting thing here is we would be doing that for both cations and anions. And the reason that we're doing that is because we really need to have electroneutrality. Electroneutrality must be maintained in solution. This again is like you can dissolve salts in water, but you don't get shocked by the water because actually the net charge balance is maintained. When we had an earlier description, we used aluminum sulfate being dissolved into water, and that's Al2SO4 and the Al2, so you had 2 moles of a 3 plus cation of aluminum ion, and then you had 3 moles of your sulfate ion, which is a 2 minus anion charge. Together that makes a 6 plus and a 6 minus equivalent of cations and anions maintaining electroneutrality. Now, as we move forward, we're going to be really focusing on 2 questions. The first one is going to be how can I estimate the activity coefficients as a mean value of activity coefficients for both cations and anions. It's effectively how do we simplify the use of activity coefficients when we're trying to find the chemical equilibrium between a salt and its dissolved ions. The second is going to be what's going to be an effect of other ions in solution on my solubility and chemical potential. So if I have a sodium chloride solution and I added a different salt into that system, what would be the effect of those other ions on the solubility of salt or the chemical potential of those ions in solution? So we're going to look at those 2 as we move on today. Activity coefficients, again, gamma, is the goal here is to think about the mean activity coefficient. And so we're doing a simplification here, and we're assuming that we have activity coefficients for the anion and the cation, and we want to, or we have estimates of that at the given concentration. And we want to know how would we average out a mean activity coefficient that would apply itself to either anion or cation. Again, this simplifies some of our thermodynamic calculations. So you're going to see a gamma with a subscript p that is positive, right, and a gamma with a subscript that is negative, both of which are referring to the cation and the anion respectively. And of course, they're also going to have their stoichiometric coefficients with positives and negatives, referring to cations and anions. And then that mean value is finally raised to 1 over the sum of the stoichiometric coefficients. And let's do that as an example. So if I were to take a really simple system, a solution equilibrium of silver chloride. Okay, I'm going to take silver chloride salt, solid silver chloride. I'm going to dissolve it in water. If I wanted to calculate the activity coefficient, I would take the activity coefficient of the silver ion raised to the 1, because I have 1 mole of silver ion, and the activity coefficient of the chloride ion raised to the 1, because I have 1 mole of the chloride ion, and the net combination of those two multiplied by each other is raised to the 1/2 power, because I have 1 over 1 plus 1. So I'd have, just looking at the very basic breakdown, that would be where I'd be tying things together. And again, this would get a little more interesting if I were to use something like an aluminum sulfate, where in the I would have 1 over 1, or in this blue section up here for aluminum sulfate, for example, I would have 1 over 2 plus 3, so I'd have 1/5. Now, if I put a salt in water, I am actually setting up a scenario at a given temperature where I have a solid in solution and I have resulting ions in solution. And let's say we have a scenario where both of them are going to be present, like a two-phase type of scenario. I have a solid phase and I have dissolved species in addition to that solid phase. So I would write the chemical potential of the solid phase on one side of the equation equal to the chemical potential of the dissolved ion species on the right side of the equation at chemical equilibrium for a solubility study. So you're seeing a chemical potential as a standard chemical potential. This would be at a 1 bar pressure and at the temperature of interest, say 25 degrees Celsius or 298 Kelvin. That's the chemical potential of the silver chloride plus RT times the natural log of the activity of the silver chloride solid. And that would be the general way that we would write a deviation from the standard state at a given temperature that we're interested in, that RT natural log of the activity. Well, here's the interesting thing. The activity of a solid is actually set at a value of 1. So any solid, the activity of that solid is set as an activity of 1, which would make that a natural log of 1. And then we know that a natural log of 1 is going to be equal to 0. So that entire part of the equation effectively gets canceled out. Let's go over to the right side where I have the dissolved ions. I'm going to take both the silver ion and the chloride ion and multiply them times 2 to effectively get that mean chemical potential for each of them. Then you see that I have RT natural log of the mean activity coefficient squared and times the molality. This would be the concentration in terms of moles per kilogram of silver chloride, of silver ion and silver and chloride ion in terms of moles per kilogram there. And we normalize that to a standard molality solution for 1 mole of the solute per 1 kilogram of the solvent. In this case, the solvent, of course, would be water. But what I'm going to do is start separating these guys apart. I've set up a basic equation of chemical potential of the solid on the left, chemical potential of the ions on the right, and now I'm going to proceed to separate some variables so that I can start to answer some interesting questions about the chemical potentials only using the mean activity coefficient. So first let's move that the 2 times the chemical potential of the ions over to the other side of the equation. We're also going to divide both sides of the equation by RT, so we isolate out the portion of the equation that is the natural log. And I'm going to take the natural log to the exponential, which is going to cancel out the natural log on the right side. It's going to create an exponential on the left side of the equation. Okay, so now see where we're going in terms of manipulating the equation. And I basically isolated this activity coefficient and molality portion of the equation. And now I'm going to move it into separate variables to show how this fits together in equation form. So the equilibrium constant for our given temperature is going to be equal to the activity of the silver ion times the activity of the chloride ion. I get that value by knowing about the mean activity coefficient of the two, that is a squared term, and then I'm going to have my molality. These are measured values of molality per standard solution. And that is all going to be equal to that. This would have been the part of the equation on the left, exponential, the chemical potential of the solid at standard state, minus 2 times the chemical potential of the ions in solution divided by RT. Okay? Once again, that black term, the chemical potential, is for the solid, the red term is for the ions, and the equilibrium constant itself is actually can be thought of in a special form because we're talking about solubility. We would also call that the solubility product, and so in say on ChemWiki or in different chemistry texts, you often see a KSP value for the equilibrium constant of dissolution. That's called the solubility product. If I look at silver chloride, let's assume that we've gone through this work. We've actually found those activity coefficients for given mole fractions to find out what is my solubility product. What is the, basically the activity squared of the silver ions times the chloride ions. It's going to be a unitless value, and it's going to be 1.8 times 10 to the minus 10 at 298 degrees Kelvin. So very, very, very small number. 10 to the minus 10 is an exceedingly small number, which again is part of why in general chemistry language we would call silver chloride a sparingly soluble salt. You're going to throw silver chloride into solution. Some silver ions, some chloride ions are going to go into solution, but the majority of the system is going to stay supersaturated. Let's compare that to our own table salt, silver to sodium chloride. It's going to be a very different system. My solubility product is going to be 3.73 times 10 to the 1. Okay, that's 11 orders of magnitude difference. That is a significantly higher value, which logically makes sense from your experience that you can take room temperature water, you can dump a lot of salt into that glass of water and it'll all go into solution, and it takes a lot of salt to finally reach the state where you are in equilibrium with both a solid in the mixture and sodium and chloride ions dissolved. Now, I want to go in between those values because those are kind of like your two extremes, a sparingly soluble salt and a highly soluble salt such as sodium chloride. So let's imagine that we want to think about environmental waters. These would be the types of waters where I have underground water running through limestone, running through dolomite, calcite. Calcium carbonate is your standard calcite chemical composition. And the solubility product of that is 2.8 times 10 to the minus 9. So it's an order of magnitude higher than that of silver chloride, but still pretty low solubility. If I were to compare that with magnesium carbonate, this also is in like your dolomite minerals in limestones. The solubility product is about 1.6 times 10 to the minus 8, so slightly another order of magnitude more soluble. If I were to combine calcium carbonate, magnesium carbonate together in normal tap water, this is basically what we think of as hard water. And it is hard is because we actually have a sufficiently high concentration of calcium and magnesium carbonate ions in solution that they precipitate out very easily at room temperature. So just pointing out another part of your everyday lives, when you have hard water, what you're dealing with is a relatively small solubility product for ions in solution and a relatively high concentration of magnesium, calcium, and carbonate that end up precipitating out in your sinks or bathrooms and the like. All right, so from a brief understanding of activity coefficients and how activity as a concept relates to solubility, we now transfer over to a basic theory of ionic solids that was constructed by Debye and Huckel for dissolving ionic solids inside of a system. So if I take salt and I add salt into water, what I am doing is that you would say that I am changing the ionic strength of the solution. You're changing the amount of charge and the concentration of ions inside of the solution. And so that concept, ionic strength, is given the value I, and it's 1/2 the sum of the ionic charges squared for each species. So say sodium would be 1 mole of sodium squared, 1 mole of calcium squared. But if we were to have, say, aluminum sulfate, we would be having the ionic charge on aluminum 3+ squared, times the molality of the aluminum ions, plus the sum of the sulfate ions squared, that would be 2- squared, times the concentration. Everything becomes positive, of course, because you have the squared value in there, and it's modified by the concentration in the system. So if I want to find or estimate the activity for my system, I'm going to find that the activity coefficients are affected by the ionic strength. So if my activity coefficient is gamma, let's frame this in a natural log format. If I wanted to find gamma, it would be what you're seeing here is the Debye-Huckel equation. And I've got values A and B going on here. Let's hold off on that for the second, but we can see that we have Z squared, which would be my ionic charge squared for a given dissolved ion. Then I'd have the square root of the ionic strength, which we already were describing can be found in terms of the sum of ions times ionic charge times their concentration, divided by 1 plus B times the square root. So let's find out what A and B are. So B is going to be a coefficient, or let's say a constant for water at 298 at 25 degrees C. It's going to be a value of just a dimensionless value of 0.33. Whereas A is going to be minus 1.17, again, dimensionless value. Okay, which then means that the only thing that I really need is the charge on the ion of interest and the ionic strength of the whole solution. And the ionic strength of the whole solution, again, I'm finding by 1/2 the sum of the charges on the system squared times the concentration as molality for each species. The aspect of, say, electroneutrality is also evaluated in terms of thinking of Coulomb's law, where the force, any force between any two charges, this is electrostatics, right, is going to be 2 point charges, their charge, times the charge on an electron squared, 4 pi divided by 4 pi times the permittivity of a vacuum, which has a constant value that we were seeing right up there, times the actual permittivity of water. And that's at about 78.5 coulomb squared per Newton per mole squared. So what am I trying to get across by conveying that the activity coefficient is deeply related to the ionic strength? Well, the activity coefficient affects the solubility, because the solubility is going to be the activity squared of my ions. So I get that, out of this I get that the solubility is affected in large part by the ionic strength, by the net ionic strength of the whole system. The activity is going to be affecting the solubility, and so the activity is affected by ionic strength, and so the solubility is affected by ionic strength. If I have, again, silver chloride as a sparingly soluble salt in solution, and if I were then to add sodium chloride, I would shift the solubility of the silver chloride. I would actually tend to make it less soluble. I'd have more salt in solution. Which is to say that the ionic strength for, say, silver chloride, the ionic strength depends not only on the concentration of the silver ions and the chloride ions, but also on whatever else I have in solution. And this is really important in environmental water chemistry and groundwater chemistry, as well as in electrochemistry for batteries and fuel cells and the like. I often will see non-participating ions in the system. They're not participating in the chemical reactions that we're interested in, or the solubility. They're not directly participating in the solubility, but because they influence and shift the ionic strength, they shift the activity, which then shifts the solubility of my species in the system. Additionally, the solubility is going to depend on all ions in solution. So the ionic strength depends on all ions. The solubility is affected by the activity, which is affected by all the ions in. And so we often would do this in the laboratory. We could precipitate out a low solubility salt or ion even more readily by just adding salt. And we actually have this happening in nature. So imagine that I have river water. Okay, standard river water is going to have relatively low ionic strength until we hit ocean waters, right? We have a river that goes into the ocean. Suddenly we have a dramatic increase in ionic strength at the river delta, and what's going to happen there? Well, we're going to precipitate out a lot of different things. We will change the ionic strength, and will affect the way a lot of different environmental chemistries behavior just at that increase and change in ionic strength. Okay, so transitioning now to thinking about ionic strength tied to electrochemistry, tied to fundamental changes in the Gibbs free energy of the system. So if I go to UC Davis's ChemWiki, they have, again, a great set of reading on electrochemistry. This particular part of their electrochemistry notebooks is about how electrochemical cell potentials depend on concentrations. Okay, so if we were to have, in this case, a zinc-copper cell, where we have a zinc concentration inside of a zinc ion, copper ion aqueous solution. If I were to reduce the concentration one way or another in that zinc-copper cell, then we're going to reduce the value of what's called it's a K value, for the cell reaction, making it more spontaneous, and ultimately if I reduce the value of the products, I'm going to make that reaction more spontaneous, and I'm going to drive it to the right. And this is really just an effect of Le Chatelier's principle. This is a driving force that I would really highly recommend you guys to go back as a task, go in, read up on Le Chatelier's principle. It's very simple, it's a very basic part, but it's a crucial part of how chemical reactions can be moved around and influenced. And it's one that a lot of people tend to miss. But here, Le Chatelier's principle is talking about concentration. If I reduce the concentration on one side, on the right side of the equation, I actually will drive the equation to the right. Another way of looking at it is if I were to increase the concentration of copper ions in solution on the left side, I would drive the reaction to the right as well. Again, a demonstration of Le Chatelier's principle. So please go take a few minutes and review Le Chatelier's principle. What we're saying in that changing concentration changes the behavior of the reaction is to build off of the concept that we already have, that a change in temperature will change the Gibbs free energy of reaction from a standard to a different potential. That would be that RT natural log of the K value. But additionally, the change in activity of one of my species is also going to change the Gibbs free energy. So when I say concentration, I'm implying in this case that I'm also changing the activity, the effective mole fraction in the system. If I change the mole fraction of one of my species, I change the Gibbs free energy of that species. If I thought about it, because activity is related to the natural log of the product of activities, right? So the chemical potential is proportional to the natural log of the product of activities raised to their stoichiometric coefficients. That's why we're getting that quotient that comes out of that, of products and reactants, is really how we're saying that change in activity changes Gibbs free energy. And really what we're talking about is Le Chatelier's principle. So Le Chatelier's principle in the deeper thermodynamics sense is expressed right here by changes in activity causing a change in Gibbs free energy, which is really an electrochemical driver. As a little reminder, we have, again, that the natural log, this is kind of rewriting what we've done before, the natural log of the product of activities raised to their stoichiometric coefficients is going to be equal to the negative change in Gibbs free energy of the reaction divided by RT. And that product value on the right is going to be all dealing with products minus reactants. So Gibbs free energy as a state function is going to be the Gibbs free energy of the products minus the Gibbs free energy of the reactants, gives me the change in the Gibbs free energy of the reaction. And I have my quotient of solubility dealing with the different activities of my participating species on the left. Now, the value here, this K, or in ChemWiki, it's also a Q, is called the reaction quotient. So that K, when it is in equilibrium, is really the equilibrium constant. But we can have scenarios, right, where we have a reaction quotient that shifts the Gibbs free energy, and it shifts it away from the standard state. So if the change in temperature changes us away from the equilibrium constant, so will a change in activities shift us away from the equilibrium constant. And of course we could have either effective pressure fugacity or effective mole fraction activity being represented here. So I've talked about measuring pressure, and I've talked about measuring concentration through mole fraction. So measuring concentration through the partial pressure, physical measurement, and measuring concentration through the mole fraction. But we actually have one more property that's available to us as a measurement, and that's measuring the electrical potential in a system. So if I have if I have any system in kind of our modern concepts, I could be measuring the potential between two electrodes. That's an electrostatic potential. Similarly, I can do that in solution with two electrodes in solution to measure a standard potential or a potential of reaction, and I can define that using standard potentials of my products and my reactants, just like I had been talking about before with activities, only now I can do that same sort of analysis with the standard potentials of products minus the standard potentials of reactants. Again, standard potential here is a voltage, and voltage is an intensive property, so no matter how many moles we have of products or reactants, we still end up with the standard potential. Tying that together to the Gibbs free energy of reaction, the Gibbs free energy of reaction is going to be opposite in sign from the standard potential of the reaction. So if I found a potential of a reaction that was net positive, I would find it to be a spontaneous reaction, because the Gibbs free energy of the reaction is going to be opposite sign of that standard potential of reaction. And a negative Gibbs free energy of reaction is a spontaneous process. So you'll see in equation 9.35 from Koretsky that basic relationship between a positive standard potential of reaction and a negative valued Gibbs free energy of reaction. What you should really see as significant in the denominator is the charge Z, and this is a Z of electrons participating in an electrochemical reaction times Faraday's constant. So that ZF is now replacing our RT reaction that we had in our prior reaction, and our prior measurements of pressure, partial pressure versus mole fraction. Let's see how that plays itself out in the last bit of our work. So if the standard Gibbs free energy change is going to be minus ZF times the standard potential of reaction, and you'll note here this N is being replaced in ChemWiki for Z, but it's the number of electrons participating in the reaction. The thing that I want to point out is that there is going to be a Gibbs free energy change of any reaction times the negative of the number of electrons participating in the reaction, Faraday's constant, and the electrostatic potential of reaction at a given condition. So we have the reference state, and we have the state being evaluated. And you'll see that similar formation of a Gibbs free energy of any given reaction is going to be equal to the standard Gibbs free energy plus RT times the natural log of the reaction quotient. Here again it's Q, but we've been dealing with it as K in a lot of our notes. And from this basic combination of those standard Gibbs free energy relationships and regular Gibbs free energy of reaction relationships, we can rewrite the equation for the Faraday's constant for both, insert them in, and then I have minus n Faraday's constant times the standard potential of the reaction plus RT times the natural log of the reaction quotient. And I can rewrite this as the electrostatic potential of the reaction is going to be equal to the standard potential of the reaction minus RT divided by NF, number of electrons, that would be ZF in a lot of our textbooks, number of electrons participating in the chemical reaction times Faraday's constant. That is all multiplied by the natural log of K, or the natural log of Q. And as a reminder, the reaction quotient itself measures the relative amounts of products and reactants present during a reaction at a particular point in time. We quite often have been dealing with it as the Q value relative to the equilibrium constant, KSP. ChemWiki just calls it K. But the interesting thing here is that equation where I'm relating electrostatic potentials times standard potential of reaction minus RT over NF, natural log of Q. That guy right there is what we would call the Nernst equation. That's a fundamental way of tying the thermodynamics of the Gibbs free energy of a reaction to the behavior of the concentration of ions in solution and the participating electrons. So effectively, this is a way that we could put in a result in terms of the change of the temperature T that we know has an effect on changing the potential or the Gibbs free energy of the reaction, or a way that we change the concentration of the products or the reactants to again cause a change in the reaction potential. This makes the Nernst equation a really powerful piece of mathematical relationships inside of thermodynamics, such that I can modify either temperature or one of my constituent species concentrations and cause a change in the Gibbs free energy of the reaction to drive it into either being more spontaneous or less spontaneous in nature, and to evaluate whether a system will be spontaneous or and it being spontaneous galvanic in nature, or being non-spontaneous and potentially being part of an electrolytic process. And I think that's all I've got for you today. We will see you in lecture next time, and good luck with your studies. Feel free to post on the forum with any follow-up questions. Thank you.